Hello and welcome to another video for Calculus 1. In this video, we are going to discuss about some basic rules of differentiation. In the previous video, we talked about the definition of derivative, and then we used the definition to find the derivative of some functions. But when it comes with the more complicated function, or even with high degree polynomial, it is really challenging using the definition to find the derivative. So now we need to come up with some rules that helps us to find the derivative in more easy way. So here are some basic rules that we are going to use. So the first one is called constant rule, where if the function is constant, so for example, f of x equals c, then the derivative is 0. That means constant function is a function whose graph is a horizontal line. Now we clearly see that the slope of that horizontal line is 0. Remember, the derivative gives us the slope, so the slope of the horizontal line is 0, that's why the derivative is 0. Now the next very important and very powerful rule that I usually call it a powerful rule is the power rule, because this is what helps a lot with those challenging types of problem, okay, where we have challenges when we use the definition to find the derivative. So if a function is f of x equals x to the nth, the power function, then the derivative is n, so we bring that exponent down here, so n times x to the n minus 1. So for example, if we have f of x equals x to the ninth, then the derivative is f prime of x equals 9x to the 8. So we subtract 1 from the exponent. We bring this exponent down, and then we subtract 1 from the exponent. So this is very important, because if we have to use the definition to find the derivative of x to the 9, that's going to be challenging. So for example, if we use the definition that it says limit h approaches 0, x plus h to the 9th minus x to the 9 over h. Now we have to expand this x plus h to the 9, which is going to be very challenging. Or you have to multiply x plus h by itself 9 times. So that's going to be really challenging. So using definition, it's really hard to find the derivative. But with this rule now, we can find the derivative just in one step. Now, similarly, there's another rule, which is the constant multiple rule. So the derivative of constant is 0. But if the constant is a multiple, or if we are multiplying a function by constant, then the constant stays as it is, and we find the derivative of the function. So for example, if we have 5x to the fifth, now 5 stays as 5, and then we find the derivative of x to the fifth, and then we multiply. Okay, so that's the constant multiple rule. Now the next one is sum and difference. So if we are finding the derivative of sum or difference of two functions, then that is same as finding the sum or difference of their derivative. So yeah, we can distribute the derivative. That's basically what it does here. So let's look at some of the examples and let's apply these rules. So the first example here is find the derivative of this polynomial function. You can see if we have to use the definition for this one, we would be doing that forever. So it's really challenging. It's like almost impossible, okay? So now what we do is we'll use these rules, so that makes it so much easy for us, okay? So we have to use several rules here. We are going to use all those rules that we had, because the first one, we are going to use sum and difference. That means we can distribute their derivative for all these terms, and then we'll use the constant multiple rule, we'll use the power rule. So we are going to use all those 4 rules that we just looked at, okay? So let me write this one as, so we have a constant, so constant times the derivative of x to the 15th minus, again, constant times the derivative of x to the 6th plus the constant 5 times the derivative of x cubed minus the derivative of 16. Okay, now that equals 2 times, so the derivative of x to the 15, we are going to use this power rule, so the derivative of x to the n is n times x to the n minus 1. So that means this is 15 times x to the 14 minus 3 times the derivative of x to the 6th is 6x to the fifth plus 5 times the derivative of x cubed is 3x squared minus the derivative of 16 is 0 because it's a constant. Now this equals 15 times 2 is 30, x to the 14th minus 18, x to the 5th plus 15 x squared plus, minus 0, so we don't have to write. So this is the derivative of this given function. Now I showed you how we apply all of the rule. Now once we get used to it, this one, we can just write the derivative directly from here to this one. Okay, so let's see how we can do that. So here what we do is that derivative equals, so we are going to bring that exponent down. So 2 times 15 is 30 x to the 14th. Now 6 times 3, 18 x to the 5th. Now 3 times 5, 15 x squared. And the derivative of 16 is 0. So we can basically go from here to here in one step. But that is how we get this. Okay, so if you have to write all these steps, that's what it is. Now let's look at the next one here. Let me erase this because I use some area here. Okay, so I will erase this and then we'll do the next one. So here, again, we do the same thing. So we'll find the derivative of the first one. So let's not show all the process. Let's do in shortcut. So derivative of pi to the 6. Don't think that we are going to use a power rule here because pi is a constant. So constant raised to a power is a constant. So derivative of constant is 0. So it's not 6 pi to the 5th. Okay, it's a constant. It's not a variable. So plus we have 2 times, so we bring that exponent here, 3/2 x to the 3/2 minus 1, which is 1/2, minus derivative of 2x is just 2 times derivative of x is 1, so it's just 2, okay? So this gives us 3x to the 1/2 minus 2. We can leave it here, or we can also write it as 3. So x to the 1/2 is the square root of x minus 2. We can also write it in this form. Either one is okay. Now let's look at more examples. So now here, we really don't have rule for radical. So what we need to do is change everything as an exponent because we have that power rule. So we have to change everything in terms of the power of the variable. Okay, so here we have square root of t. So we'll change that in the power form. Okay, so what we do here is, so first let's go ahead and write it this way. So derivative of 3 over 8. So square root of t, we can write that as t to the 1/2 minus, so this one we have 2 over square root of t, which we can write 2 over t to the 1/2, and then if we put it up here, we can write that as 2t to the negative 1/2. So remember this rule, a to the m can be written as 1 over a to the negative m, or a to the negative m can be written as 1 over a to the m. So we are using this rule here. We're going from here to here, okay? So that means this is minus 2t to the negative 1/2 plus t squared minus 7. Now, if we find the derivative, now this is 3/8. Derivative of t to the 1/2 is 1/2, so that power comes down here. Then t to the 1/2 minus 1, which is negative 1/2, minus 2 times negative 1/2 t to the, so we already have negative 1/2, and when we subtract 1 from negative 1/2, we get negative 3/2, plus 2 times t minus 0, because the derivative of 7 is a constant, so it's 0. Now let's go ahead and simplify this. So this is 3 over 16. Again, we have a negative exponent. Usually, we would like to write that as a positive exponent, but let's write it this way first, and then we'll change it to a positive exponent. Okay, so t to the negative 1/2 plus 1, because 2 and 2 cancels out, so t to the negative 3/2 plus 2t. So if you leave it here, still this is the right answer. There's nothing wrong here. But usually we don't want to write it as a negative exponent. So what we do here is, again, we use the same rule. If we have a to the negative m, then we can write that as a to the m, okay? So 3 over 16t to the 1 half plus 1 over t to the 3 half plus 2t. Or we can also rewrite this as 3 over 16 square root of t plus 1 over t to the 3 half plus 2t, and we'll just leave it here. Now let's look at the next example. Okay, so in this next example, first what we are going to do is we will distribute that common denominator among the terms. So what we are going to do is we will write minus 5x squared over square root of x means x to the 1 half. Okay, then minus 6x over x to the 1 half plus 2 over x to the 1 half. Now let's put everything in the top. So d over dx, then we have minus 5x to the, so we have 2 minus, so 2 minus 1 half when we simplify that, so we get 3 half here, minus 6x to the 1 half plus 2x to the negative 1 half, because we don't have x in the numerator. When we take that up here, that exponent becomes negative. So now we'll find the derivative. So we have negative 5 times, we bring that exponent down, so 3 half x to the 3 half minus 1, which is 1 half, minus 6 times 1 half x to the negative 1 half plus 2 times negative 1 half x to the, so negative 1 half minus 1 is negative 3 half. So that equals, so this one, the first one becomes negative 15 over 2. So we can write that as square root of x minus, this is 3 over x to the 1 half, which we can write as square root of x, minus this is 1 over x to the 3 half, because we have a negative exponent, so we'll make it positive. And then we'll just leave it here. Now I want you to try this problem on your own. You can pause the video and then resume the video after you're done, and then you can check your work, okay? Let's go ahead and do it now. So this equals d over dx. Again, let's change that radical into an exponent. So remember this, if you have nth root of a to the n, so that is a to the n over m. That's how we change this radical into an exponent, okay? So same thing here, we have x is 2 over 3, then minus x to the 1 half plus 5x minus 2. And then when we find the derivative, so the derivative of the first one is 2/3 x to the, now we have to do 2/3 minus 1, which is negative 1/3. Okay, so 2/3 minus 1 is negative 1/3. Minus, so 1 half x to the negative 1 half plus 5. And then that becomes, we have 2/3, and we can make it positive by putting that underneath in the denominator, minus, so we can do the same thing here, 1 over 2 square root of x, because x to the 1 half is the square root of x, plus 5, and then we can leave it right here. Okay, so let's look at next example. Now, remember this question we started, when we started the first video, we had this question. We estimated the slope of the tangent line by making table. And then next, in the last video, we did the same problem. We found the derivative using the definition, and we found the slope. Now, this is what we were exactly looking at now. We can do this in such an easy way that we can do this in like 2 to 3 steps, okay? So the first thing is, to find the slope of the tangent line, we need the derivative. Now, if we use the rule of the derivative, then we have that f of x equals 2x squared. Now, if I find the first derivative of this function, I get 4x. See, when we did using the definition, it was almost like a page, right? Almost page long. But now we got that in one step. Now, the slope of the tangent line, slope of the tangent line at x equals 1 is given by is m equals f prime at 1, which is 4 times 1, and that is 4. The slope is 4, and that's what we had earlier. Now, we need a point and the slope to find the equation. So we got the slope. Now, the point where we are finding the tangent or the point of tangency is, so we have the x value, which is 1, and the y value, when you plug that in here, we get 2. Okay, so that's the y value. Now let's go ahead and find the equation. So we will use the point slope form of the equation. So the equation of the tangent line at x equals 1 is given by y minus y1, which is 2, equals m, which is 4, times x minus x1, so x minus 1. And that gives us y minus 2 equals 4x minus 4. And that when you add 2 on both sides, so we get y equals 4x minus 2. And that's the exact equation that we had when we did this problem earlier. Now see, this became so much easier with these rules of derivative now, as compared to when we did this using table and then using the definition of derivative. Now, you can pause this video and then you can try this example and then check your work, okay? So now this problem is asking you to find the points on the curve of that function where the tangent line is horizontal. So this is very important, okay? The tangent line is horizontal. So let's talk about that. When the tangent line is horizontal, that means it's a horizontal line. The slope of the horizontal line is 0. So basically it means wherever the tangent is horizontal, the slope is 0, which means the derivative is 0. That's what we have to look at, okay? So horizontal tangent line means the slope of the tangent is 0. The slope of the tangent is 0 means the first derivative is 0. That's what we are looking at. So what we need to do first, we have to find the derivative of this function. So let's go ahead and do that. So y equals, so we have y equals 2x cubed plus 3x squared minus 36x plus 5. Now let's find the derivative. Dy over dx equals 6x squared plus 6x minus 36. Now the tangent line is horizontal at x if 6x squared plus 6x minus 36 is 0. So that means this derivative is 0 wherever the tangent line is horizontal. So derivative 0 means slope is 0, okay? Now we just have to solve this equation to find the x values. So we're going to divide everything by 6. So that gives us x squared plus x minus 6 equals 0. And then we can factor this easily. So it's x plus 3 times x minus 2 equals 0. And then we get x equals negative 3 and x equals 2. So those are the two x values where the tangent line is horizontal. Now we have the x values. Now we need to find the y values. So what we do is we will get our calculator and then we'll put this into our function to find the y value. Okay, so when x equals negative 3, y equals 2 times negative 3 cubed plus 3 times negative 3 squared minus 36 times negative 3 plus 5. And then you can put this into the calculator. We can do it by hand. So negative 3 cubed is negative 27, okay? And then when we multiply by 2, we get negative 54. Then negative 3 squared is 9 times 3 is 27, which is positive. Now negative 36 times negative 3 is 108, so plus 108 plus 5. Now if we add those numbers, so we have negative 54 plus 27 plus 108 plus 5, and then that gives us 86. So the first point where the tangent line is horizontal is negative 3 comma 86. So similarly, when x equals the other point, which is 2, so when x equals 2, okay, the y value is y equals 2 times 2 cubed plus 3 times 2 squared minus 36 times 2 plus 5. 2 cubed is 8 times 2 16 plus this is 12 minus this is 72 plus 5. And then if we put this into our calculator, is 16 plus 12 minus 72 plus 5 gives us negative 39. So the points that we are looking, okay, are negative 3 and 86, okay, and the other one is 2 and negative 39. So these are the 2 points where the tangent line is horizontal. You can just draw the graph and you'll probably see at this point you'll have a peak or dip in that function, okay? Now, we know that a number e, the Euler number e equals, says this is the value. It is not terminating decimal, so it goes forever. But this limit is true, okay? We're not going to prove it, but we are going to use this. So limit is h approaches 0 of e to the h minus 1 over h equals 1. That's always true. Now we are going to use that to find the derivative of the function e to the x. So it's here, it says the derivative of e to the x is e to the x, so derivative itself. So now let's go ahead and prove that the derivative of e to the x is e to the x. So first, in order to prove that, we are going to use the definition. So we know that the definition for the derivative is limit as h approaches 0 of f of x plus h minus f of x equals h. So this limit gives us the derivative. Now here f of x is e to the x. That means f of x plus h is e to the x plus h. So let's go ahead and use this definition. So f prime of x equals limit as h approaches 0. So f of x plus h is e to the x plus h minus f of x is e to the x divided by h. Now let's use the rule of indices here. So e to the x plus h, we can add e to the x times e to the h minus e to the x over h. Now if we factor out e to the x from the numerator, and we can pull it all the way out here, e to the x, because the limit is h approaches 0, it's not x approaches 0. So we can pull that e to the x out, and then we can write limit h approaches 0 of e to the h minus 1 over h. When I factor out e to the x, so the numerator becomes e to the h minus 1. Now we have this definition up here. This limit right here is 1. So if that is 1, then that equals e to the x times 1, which is e to the x. So basically, we got that derivative of our function e to the x is e to the x. So that's how we prove that, okay? Now we're going to use it. So here, given f of x equals 3x minus e to the x, find an equation of the tangent to the graph of f at x equals 0. So that's what we are trying to do next, okay? So let's go ahead and find the slope because we want the tangent line. So the slope is given by the first derivative. So f of x equals 3x minus e to the x. That means f prime x equals 3, because derivative of 3x is 3, minus derivative of e to the x is just e to the x. Now our slope of the tangent line is given by, so we are finding slope at x equals 0. So slope is f prime of 0 equals 3 minus e to the 0, which gives us 3 minus 1, and that is 2. So that's our slope. Now we need a point. We have the x value. So the y value is, we plug that in here, okay? So 3 times 0 is 0, minus e to the 0 is 1. So basically the point where we are finding the tangent line is x is 0, y is, so 3 times 0 minus e to the 0, which is 0 minus 1, equals negative 1. So the y value is negative 1. Now we have the point, we have the slope, so we can find the equation of the tangent line using the point slope form of the equation. So y minus y1 equals m, which is 2, times x minus x1. So that gives us y plus 1 equals 2x, and then if we subtract 1 on both sides, we'll get y equals 2x minus 1. So this is the equation of the tangent line to this curve at x equals 0. Now the second equation is asking us to find the points on the graph of f where the tangent line is horizontal. Again, tangent line horizontal means the slope is 0. Slope is 0 means the first derivative is 0. So the tangent line, so this is part B, the tangent line is horizontal if the derivative, so f prime x equals 0, okay? So f prime x is 3 minus e to the x equals 0. And then if we take e to the x on the other side, so we get e to the x equals 3. And then if we solve for x, we get x equals natural log of 3. So that is the x value. So if x value is natural log of 3, the y value is y equals, we have to put it into our function, which is 3x, means 3 natural log of 3, minus e to the natural log of 3. And then you know that e to the natural log of 3 is just 3. So 3 natural log of 3 minus 3. We can just leave there, okay? So this is the x value, this is the y value. So the point where the tangent line is horizontal is natural log of 3 comma 3 natural log of 3 minus 3. And if you want, you can change it to the decimal, but I'm just going to leave it exact like that. So now we could have higher order derivative. Okay, so the one that we were doing was the first derivative. Now if we find the derivative of the first derivative, that becomes the second derivative, and this is how we denote that by f double prime. Okay, and then if you find the derivative of the second derivative, then we get the third derivative. And we can continue that until it's as long as it is possible, okay? Sometimes it might be impossible. We might get 0. Then after that, everything is 0, always 0. So, but as long as we can find it, as long as the derivative exists, we can find the higher order derivative for a function. And the notation, this is another notation. So we have d2f over dx2, okay? And for the third derivative, similar d3f over dx3. Then if it's the nth derivative, we just denote this by f to the nth, which means nth derivative of f at x, okay? Now let's look at some example. So this one is asking us to find the second and third derivative. So this is second and third derivative of the following functions, okay? Uh, Now, in order to find the second derivative, we must first find the first derivative. Without first derivative, we cannot find the second derivative. So what we need to do is we have to find the first, then we'll find the second, and then we'll find the third. So this is the function. Let's go ahead and find the first derivative. F prime of x equals, so same thing that we did earlier. So 4 comes down. So 5 times 4 is 20 x to the third. Remember, we subtract the power. We subtract 1 from the power. Okay, so 3 comes down, that's minus 9 x squared. 2 comes down, plus 10x. And then there's this 1, so 16, and then derivative of x is just 1, and then minus 0, because derivative of 2 is 0. So we don't even have to write this. So we can just erase that. Okay. Now, let's go ahead and this is the first derivative. So this is called the first derivative. Now let's go ahead and find the second derivative. Second derivative means f double prime of x equals, we just find the derivative of this function, or the first derivative. So this is 60x squared minus 18x plus 10. So this is the second derivative. Okay. Now let's go ahead and find the third derivative, which means we'll find the derivative of this function. F triple prime of x equals, so this is 120x minus 18. And this is the third derivative. So that's how we can find the higher order derivative. Let's do the same thing for this one. Let's go ahead and first find the first derivative. So dy over dx for this function is, so bring that 2 down, so we have 4x minus constant times e to the x, so 7, the constant is constant, times derivative of e to the x is just e to the x. Remember, the constant, when it comes with the function, is just the constant multiple. We keep constant as it is. But if it is by itself, if the constant is by itself, then the derivative is 0. So this one equals, or the six, so this is the first derivative. Now the second derivative, we write d2y over dx2 equals, so derivative of 4x is just 4 minus, again this is a constant multiple, so 7 times derivative of e to the x is e to the x. Now let's go ahead and find the third derivative. So d3y over dx3, and derivative of 4 is 0. So 0 minus 7, so it's negative 7 e to the x. Now if we keep finding the higher order derivative, we are just going to get negative 7 e to the x forever for this function, okay? Because the derivative of e to the x is just e to the x, and it's a constant multiple, so it's not going to change. So that becomes the derivative forever if we keep going on. But we'll just stop here. So this is the third derivative, this is the second derivative, and this is the first derivative. Let's look at a small application here. Remember, we talked about the velocity problem at the beginning, and then we were trying to find the instantaneous velocity. So now with all this, having this derivative in hand, now we can do that easily, okay? So for example, s of t represents is a position function of any moving object. Then the velocity at any instant, any time t, is given by the derivative of the position function, which is same as the, so if this is a position function, okay, now the slope of the tangent line at a point gives us the instantaneous velocity. So the derivative gives us the slope of the tangent line at a point. So that gives us the velocity, or this is the velocity function, okay? Similarly, the acceleration is the rate of change of velocity. So acceleration is given by the derivative of the velocity or the second derivative of the position function, which is s double prime of t. So let's just look at an example for this one. So here's the function that represents the motion of an object, okay? And then we want to find the velocity function. So here the position function s of t equals 2t cubed minus t squared plus 3t plus 2. Now the velocity represented by v of t is the first derivative of the position function, which is 6t squared minus 2t plus 3. Now the acceleration represented by a of t is the first derivative of the velocity or the second derivative of the position function, which is 12t minus 2. So our velocity function for this um, problem is 6t squared minus 2t plus 3, and the acceleration function is 12t minus 2. Now what it does is, now if I want to find the velocity at some point t, then I can just plug it in here, and that gives me the velocity at that point. Or if I want to find the acceleration at t equals 5, I just plug it in here, and that gives me the acceleration as at t equals 5. So these functions are very useful when we're finding the acceleration and velocity at different points, so that we don't have to do that for each problem. Okay, once we get the function, we just substitute for t, and then we get the answer. So that's all for this video. In the next video, we'll look at some other rules of differentiation. We just look at the basic rules here. Okay, and yeah, I'll see you again in the next video.